Welcome to AI versus Nature's Fury, a strategic insights report exploring what might be possible if artificial intelligence could predict natural disasters more reliably. Over the next slides, we'll walk through current limits, promising AI methods, real-world case studies, and the practical steps needed to turn early warnings into measurable reductions in harm and economic loss. This page highlights the limits of current numerical weather prediction. Coarse grid resolution, manual tuning, lagging feeds, and missed local topography all create inefficient outputs, while wide ensemble uncertainty makes evacuation windows vague and erodes public trust. The graphic shows how these technical gaps cascade into delayed decisions and wasted resources when predictions fail. Here we survey AI methodologies that are improving forecasts, from convolutional networks that analyze satellite imagery to spot wildfire smoke and cyclone eyes, to graph networks that model river basins and hydrology, and transformers that ingest seismic time series to learn nonlinear relationships, collectively cutting prediction errors and capturing dynamics too complex for explicit equations. This flowchart outlines an AI-driven alert optimization process where synthetic storm tracks and modeled fault ruptures feed policy optimization under constrained budgets, balancing false alarms and missed events while adapting to climate drift, ultimately aiming to reduce measurable economic losses by steering interventions more precisely and efficiently. These case studies show concrete impact. Australian bushfire models can forecast ignition risk up to 3 weeks ahead with about 85% accuracy, enabling a preemptive action window, and Google's Flood Hub covers hundreds of millions, delivering roughly 7 days' notice in some regions, and saving tens of millions in agricultural losses by guiding harvest and sandbag placement. On predictive performance breakthroughs, deep learning systems in Tokyo show superior accuracy and faster aftershock location predictions compared with traditional Coulomb models, while the LSU P2M hurricane surge framework runs a 72-hour simulation on a laptop in seconds, outperforming supercomputers and providing roughly 12 extra hours of evacuation lead time for coastal counties. Retrospective benchmarks look impressive, near 97% for hurricane tracks, 89% for tsunami scenarios, 85 to 91% for floods, and high accuracy ranges for quake magnitude. But the slide reminds us these figures come from peer-reviewed, retrospective tests, and that real-time performance is limited by data quality, probabilistic outputs, and operational gaps. AI brings speed, slashing response times, and delivering warnings faster by an average of several hours in this slide, noted as roughly 3.7 hours. But managing rare extreme events remains challenging because training distributions rarely cover those. Tails. The practical answer is ensemble blending that pairs AI models with physics-based simulations and human expert oversight to preserve reliability. This slide maps key data and coverage vulnerabilities. Sparse sensor networks in rural tropics, sensor outages during disasters, and biased historical records can generate false negatives for vulnerable communities. Emerging fixes include synthetic data generation and crowdsourced phone sensors, yet all of these demand rigorous validation and calibration before they can be relied upon operationally. Trust is the core barrier to operational uptake, driven by forecaster hesitation and legal concerns around black box models. Building confidence requires interdisciplinary education, explainable AI dashboards that surface reasoning, and shared code repositories for collaborative validation so that models can be integrated into protocols with transparency and accountability. A real-time prediction and alert ecosystem depends on dense, rapid data acquisition, next-gen accelerators, nanosatellites, and IoT meshes feeding continuous model updates followed by continual AI-driven risk localization and personalized alerts delivered to devices, with the goal of getting actionable warnings to people before shaking, surge, or flooding actually begins. Finally, the promise of algorithmic civil protection is to shift response from reactive rescue to proactive prevention by 2030, pairing AI with governance and ethical frameworks to cut disaster mortality by around 30% and reduce economic losses by tens of millions per event. provided data sharing, validation, and strong ethical guardrails are in place to guide implementation.